RP2, we got a feel for the meaning of speed and velocity. Now is the time to define these little beasties more carefully. We'll start by doing something weird. We'll constrain movement to one dimension. That's motion in a straight line, either forward or backward. If we can describe one-dimensional motion, then maybe it won't be too hard to step up to 2 dimensions, and ultimately to reality, to a 3D universe. One dimension means one coordinate axis. Let's call it the x-axis. And let's be clear that x is a position, but it is also a distance measured in meters. X denotes a position and distance relative to the 0 point on the axis, the so-called origin of the axis. By convention, positions to the right of the origin are positive. Positions to the left are negative. We label the axis with an x on the positive side, and we put the units of measurement, meters, in brackets alongside the variable. By the way, in mathematics, x can stand for any quantity. Units are not assigned to that quantity because any quantity might have any units. But this is physics. Each variable stands for a unique physical quantity. In physics, x stands for distance, and by global convention, the units of distance are meters. Consider the position x equals negative 50 meters. Notice that the absolute value of x tells us the magnitude of its distance from the origin, and the sign of x, positive or negative, tells us the direction of x relative to the origin. This means that x is a vector quantity, meaning it can be represented by an arrow. Any physical quantity that, like an arrow, has both magnitude, that is length or size, and direction is a vector quantity. Position is a vector quantity. As we shall see, so are displacement and velocity and force, and there are many others. Quantities that don't have direction, that have only magnitude, that you're not tempted to represent with an arrow, are called scalar quantities. Examples of familiar scalars are mass, time, speed, and temperature. Since temperature can be negative, you might think that temperature has direction, and so is a vector quantity. But don't look for vectorhood in the numerical sign of a quantity. Scalars can be negative. Instead, think about direction in the context of the real 3D world. If you feel the urge to point when you're describing a physical quantity, then it's a vector. If you want to use an arrow to describe a quantity, then it's a vector. Force is a vector quantity because 10 newtons of push must be exerted in a certain direction. But temperature is a scalar because 20 degrees Celsius has nothing to do with direction. It's not described by an arrow. I don't have the urge to point when I say 20 degrees. When an object moves from one position to another, its x value changes, and it has been displaced. To compute this displacement, we take the later position and subtract the earlier position from it. X subscript later minus x sub earlier. For convenience, we call the earlier position the first position, and the later position the second. By the way, if you need to see some real concrete numbers here, we'll do an example very soon. But first, let's use algebra to describe the situation generally, symbolically. This is the power of algebra. We can describe an infinity of situations with just a single symbol. If you're uncomfortable with algebra, find a good math teacher, human, book, website, or app, and get hold of the basics. We'll need algebra often in radical physics. The object's displacement, when it goes from x sub 1 to x sub 2, is just the difference between these two x vectors. X sub 2 vector minus x sub 1 vector equals displacement equals delta x vector, where the Greek letter capital delta, the Greek uppercase D, stands for difference, and it reminds us to subtract. The arrow above the delta x tells us that displacement is a vector quantity. Like position, displacement has magnitude and direction. The magnitude of the displacement is the number of meters of distance moved, and the direction is either positive or negative, that is, either to the right or the left along the axis. This is really much easier than it seems. Here's a familiar example from RP2. Usain Bolt's famous 100-meter dash at the 2008 Beijing Olympics. We'll let Bolt's path define the x-axis, and his starting position will be the origin. Then Bolt's x sub 1 is 0, and x sub 2 is plus 100 meters. Clearly, delta x vector is plus 100 meters, that is, 100 meters in the positive direction. But we're trying to find velocity here, remember? So we have to think about the change in time, too. At position x sub 1, the clock read t sub 1 equals 0. And as Bolt crossed the finish line at position x sub 2, the clock read t sub 2 equals 9.69 seconds. Notice that these time values are not vectors. They are scalars. They have no direction. Now let's use the entire definition of velocity to calculate Bolt's velocity during the Beijing Olympic 100-meter dash. Velocity is defined as displacement, delta x vector, divided by the corresponding change in time, delta t. V vector is defined as delta x vector divided by delta t equals x sub 2 minus x sub 1, all divided by t sub 2 minus t sub 1. That's plus 100 meters minus 0, divided by 9.69 seconds minus 0. That's plus 10.3 meters per second. Usain Bolt's velocity vector was pointing to the right, and it had a magnitude of 10.3 meters per second. That's fast. But wait a minute. Was this Bolt's velocity at the start of the race, at the middle, or as he crossed the finish line? At the start, he was barely moving, and at the middle and end, he was flying. That plus 10.3 meters per second must describe only his velocity averaged over the whole 9.69 seconds. Yes, what we have defined here is average velocity, denoted with the subscript AV. V vector sub AV equals delta x vector divided by delta t. That is the formal definition of average velocity, so I'll box it in. Then in brackets, I'll show the units that we'll almost always use. I put them in brackets only because I don't have to use meters per second. Any distance and time units, when divided, give velocity units. But in radical physics, as in nearly all the world, we'll stick to common international units. Average velocity is measured in meters per second. While an average velocity of plus 10.3 meters per second is impressive, Bolt's maximum velocity had to be even higher. Is there a formula for that? To get close, we have to understand the concept of instantaneous velocity, velocity at an instant. The symbol for instantaneous velocity just drops the average symbol. It's simply v vector. How do you actually measure instantaneous velocity? The key is, as the name implies, is to measure the displacement over an instant, a very short period of time. We write it this way. Velocity vector equals lim delta t approaches 0 of delta x vector divided by delta t. This is read, instantaneous velocity is defined as the ratio of displacement to elapsed time in the limit as the elapsed time approaches 0. That expression, in the limit, is a little magical. For a physicist, it means let the time of displacement measurement, delta t, be very, very small. But for a mathematician, it means something more esoteric and more rigorous. This is something that lies at the heart of differential calculus. For our purposes here in radical physics, it will be enough if we understand the concept of instantaneous velocity. It is a measurement of average velocity over a very short period of time. If we want something to remember, and I hope we do, let's remember what was boxed in earlier, namely the definition of average velocity. V vector sub AV is defined as delta x vector divided by delta t, probably in meters per second. There's another way of saying all this that can be very helpful. Velocity is the rate of change of position. Not only do those words capture what we mean normally by velocity, but those words are precisely accurate if we interpret rate of change to mean what is described by delta something divided by delta t. That delta divided by delta t is called an operator. When it operates on any physical quantity, it symbolizes the rate of change of that quantity. That's very handy. Remember that. Velocity is the rate of change of position. But what about speed? Average speed is easier to define than average velocity. That's because we really don't have to take direction into account. Speed is a scalar quantity. Average speed is just what we described in RP2, although we didn't say average back then. Average speed is defined as V sub AV means distance traveled divided by elapsed time. And instantaneous speed is just the same thing, but measured over a very short period of time. By the way, Usain Bolt's greatest instantaneous velocity during that legendary 2008 gold medal dash was plus 12.2 meters per second. That's about plus 44 kilometers per hour and is slightly more than plus 27 miles per hour. He reached that maximum velocity at about the halfway point. We'll describe and understand changing velocity when we consider acceleration in episode RP7. What you'll most want to remember from this episode, RP6, is velocity is the rate of change of position. V vector sub AV is defined as delta x vector divided by delta t in good old meters per second.